Ladies and gentlemen, welcome to 20th World Congress of Psychophysiology. This year, it is video conference. Our symposium is Effective Computing and Effective Neuroscience. My name is Jingjing, the chair of this symposium, from East China University of Science and Technology. Dr. Zheng Liang is the co-chair from Shenzhen University. Emotions are an important and inseparable component in the human daily life and are contingent on internal or external events such as personal well-being, social relationship, decision-making, and behavior. Currently, affective computing has become one of the most important and active research fields that creates and brings new ways to interpret, recognize, process, and simulate human emotions. Index multidisciplinary knowledge spanning psychological, neuroscience, biomedical engineering, artificial intelligence, and so on. Emotion intelligence, together with brain science technology, offers an attractive approach to study basic neural mechanisms behind the various mental health problems, provides a direct measurement to real-time monitor emotion changes, invents new solutions to recognize and regulate human emotions, and offers a possibility to human beings to have better awareness of their own emotional health. In this symposium, the presenters will introduce the latest effective computing and effective neuroscience studies, the proposed effective brain models, the developed effective brain regulation technologies, and the built effective brain-computer interfaces. Here, we invited 5 speakers: Professor Wan Zhenkong from Hangzhou Dianzi University, Professor Xiaochu Zhang from University of Science and Technology of China, Professor Qi Li from Changchun University of Science and Technology, Professor Jianjun Meng from Shanghai Jiao Tong University, Dr. Zheng Liang from Shenzhen University. Now, let's start the talk.
Thanks very much for Professor Jingjing inviting me to have a presentation. My topic is research on task-free blueprint recognition. I'm Wan Zhenkong from College of Computer Science, Hangzhou Dianzi University. My topic will introduce from 3 aspects. The first one is face synchronization and brain network. It is a signal processing method. The second is low rank matrix decomposition. It is a traditional machine learning method. 3 is deep learning for blueprint recognition. First, background. The traditional of the identification method are mainly focused on the fingerprint, face, iris, palm print, and the disadvantage of this method are tempered, copied, or forced to use easily. Sarah in Binghamton University have proposed blueprint, a unique, collectible, and persistent EEG signal feature produced by the brain, which can be used for the identity recognition and verification. The advantage of the blueprint is unable to steal, unable to forge, and must be living body. Blueprint recognition methods usually need external stimulation or subject's cooperation to perform specific mental tasks, which are mainly divided into the following 4 categories. The first one is resting state. The second is visual evoke potential. The third, motor imaginary. The fourth, event-related potential. However, all the above EEG identification research methods can only identify the EEG signals corresponding to their respective tasks. However, the subject's cognitive state is uncontrollable and uncertain, which poses a great obstacle to the practical promotion for EEG identification. In view of the above problems, we propose a new topic of task-independent brain pattern recognition to deal with such kind of problems. Let's go to part 2, face synchronization and blueprint. The scientific basis lies that let the Hilbert transform of the continuous time signals be x hat t, and so we can get the analytic signals of xt, and it also can be divided into two parts. One is instantaneous amplitude ah and the second is the instantaneous phase part theta ht. So we can calculate the mean phase coherence and the phase locking value. So why the PS can work as a blueprint? The phase synchronization of EEG signal reflects the difference properties of brain white matter, and the phase differences are often used to estimate the nerve conduction velocity and the synaptic integration time. And the advantage of the PS is that it can detect the integration of the signal pairs by only examining the relationship between the signals, but nothing to do with their amplitude. In the construction of the network, the strength of functional connectivity between the nodes is given by the Wij. The symmetric matrix W is used as an adjacency matrix of the brain network. According to the graph theory, we can calculate the property of the brain network, such as the degree of the nodes and global effectiveness and the clustering coefficients. The average PLV is used as the weight of the brain functional network connections, and the attributes of the brain network are combined into a feature factor for identification. And the detailed step is as follows. We test our method on four different datasets. The first two are public, and the rest two are from our lab. This figure shows the brain topographic map of each subject, and the distribution of the connection of genes for each subject showed significant differences. And to make the experiment more convincing, the mean vector of node degree and the interclass dispersion matrix are calculated for each subject. From the experiment, we found that the significant inter-subject class differences with small inter-subject class difference. So we have tested our method on the dataset. This table shows the classification result of brain network with different attributes, and a single attribute we only with node degree can achieve the satisfied performance. And this table shows the feature consisting of brain network attributes work well for identity recognition on different datasets with stable accuracy. And table 3 shows the comparison result of three different methods on three different datasets. It demonstrates that our method is much better than the other method. And this figure shows the property of the brain network in beta and gamma. This high frequency band have better performance than in the low frequency band. Now let's summarize that. The phase synchronization achieve good recognition result on the dataset of different tasks, and it can also have more accurate in the high frequency band than in the low frequency band for the identification. Let's go to part 3, low rank matrix decomposition for blueprint recognition. The inspiration of the low rank matrix decomposition is stem from the image processing. Face images under different illumination conditions are composed of background, foreground, and foreground and noise part, three parts. And a study by Bergson showed that the brain has also a background EEG, a spontaneous fluctuation in neural activity, and people's cognitive decision is to insert a random effect on it. Based on this, we use low-rank sparse decomposition of EEG signals like this, and the primitive EEG signals can be decomposed by the low-rank background and the sparse task awareness EEG and noise, these three parts. However, it is usually difficult to extract the features of non-stational EEG signals in time domain. So in order to extract the relatively stable background EEG signal, we convert EEG of time domain to frequency domain for analysis by the short-time Fourier transform. And the Godek algorithm is applied for this model, and the detail is listed on this. And the main steps for the low-rank matrix decomposition is three steps. The first one is we use the training sample to reconstruct a subspace. Second is we use this subspace to generate the reconstruction for each pins for each samples. And the last step is that we use the MCC for the classification. The general flowchart of EEG identification based on LRMD is as follows. Currently, a few datasets collect under various tasks with the same subject. Therefore, we established a multitask experimental dataset called MTED, and the experimental paradigm is shown in the below. This method is verified on 4 different datasets: BCI, P300, SEED, and MTED. And this figure shows the results of EEG spectrogram decomposition of 5 subjects on P300. And the detailed code and dataset can be found on the WebGIS like this. And these tables show that our method performance on the BCI, P300, and SEED, these 3 public datasets. And this table shows our method on our own dataset MTED. It demonstrates that the method can achieve very satisfied performance. So let's summarize. The first one is the feasibility of the extracting background EEG for blueprint recognition is verified. Second is the low rank of background EEG is verified. Go to part 4. The disadvantage of the traditional machine learning mainly lies 2 points. The first one is it cannot extract the feature sufficiently. The second is it relies too much on the prior knowledge. And while the advantage of the deep learning can effectively capture high-dimensional feature and the potential relationship through the deep structure with less prior knowledge. Of course, the drawbacks is also exist for the deep learning, such as large model parameters and high requirements for device memory. For the problem of the real-life blueprint recognition lies 2 points. The first one is a large set of subjects, but a small amount of the subject samples. The second is large model parameters, but insufficient training samples. To deal with such kind of problem, so we want to use the TensorNet to convert the dense weight matrix of the fully connected layers to the tensor tree format, such that the scale of parameters and the training time is reduced hugely. And these figures illustrate that why the tensor chain can reduce the parameters hugely. And we propose the convolutional tensor chain neural networks called CTNN to explore high-dimensional interactions with local features with much less parameters to better tackle the classification task. We tested the CTNN on 4 datasets, and the EEG MMI with resting state dataset is with 105 subjects and 120 samples per person. The samples of each class is much fewer than other datasets. And for the datasets with huge set of subjects and limited subject samples, the performance of CTNN has more obvious advantage. And compared with the other CNN-based method, the CTNN has can reduced about 1,000 times parameters. Utilizing the low-rank feature of blueprint, it can be represented by the low-rank tensor with fewer parameters to effectively recognize the blueprint. And comparison with the different frequency bands, the experiment demonstrates that the blueprint recognition accuracy is in high frequency band is better than in the low frequency band, and it is consistent with the phase synchronization method. This is the visualizing of the spatial convolution kernel. We want to find which region of the brain is significant for the print recognition. And finally, we select FZ, FC1, FC2, CZ, CP1, CP2, PZ rather than 32 channels can achieve the equivalent equivalent result. Let's summarize. The CTNN performed well even with a small number of parameters, which solves the problem of model overfitting. And the blueprint information is mainly concentrated on the high frequency band. And we also primarily verifies the feasibility of the realizing blueprint recognition via several selected channels. Let's go to part 5, prospect of the blueprint recognition. In order to promote the blueprint recognition in the real life, there are three issues that should be well studied. The first one is we should develop a transfer learning method to overcome the problem of the blueprint for the cross time and cross subjects. Number 2 is we should establish a standard to decentralize the EEG acquisition device from different companies. And the last is we should find the reliable blueprint character in huge number of the subjects. We should thank Professor Babiloni, Professor Chowsky, Professor Oswald, Professor Zhou, and Professor Chor, and all the team members in my lab. Thanks very much.
Hello everyone, I'm Xiaochu Zhang from University of Science and Technology of China. My report title is Alpha Oscillatory Activity Causally Linked to Working Memory Retention, extracts from online phase-corrected closed-loop TSS. First, I will introduce the background of this research. Working memory is foundational for a wide range of cognitive function. So, investigate the neural basis of underlying memory has been a focus of neuroscience research. In fact, working memory can be further subdivided into 3 sub-processes, including retention and retrieval. Previous EEG studies have demonstrated that the relationship between the alpha oscillatory oscillations and working memory retention. Main finding is that alpha activity in the occipital parietal areas increased during the memory retention. Moreover, this is a parametric increase in alpha power with memory load during the retention. However, this study are correlations. We want to directly demonstrate the causal role for the alpha oscillations in working memory retention in humans. TSS provides us with the opportunity by non-invasively modulating endogenous alpha oscillations. The rationale behind the TSS effect is the entrainment of endogenous brain oscillations imposed by actually implied electric field and target frequency. But the entrainment effect of TSS not always be replicated in some studies. Some Research speculates that the inconsistency across this TCS study may be due to the open loop stimulations delivered without considering the phase difference between the TCS waveform and the concurrent brain oscillations. Recent computational modeling work shows that out-of-phase TCS would suppress the endogenous oscillations within a short period of time. Furthermore, Britain delivered trauma frequency TSS over the motor cortex, the Parkinson patients, and found that the tremor amplitude was clearly dependent on the phase alignment between TSS and tremor signal. This indirect evidence suggests the effect of the phase difference between the TSS effect, but we still need direct evidence. Moreover, the three different sub-processes of encoding, of working memory, the encoding, retention, and retrieval are differently related to the change in alpha oscillatory activity. Contrary to the retention, decreased instead of increased alpha oscillations during the encoding and retrieval may be beneficial for the performance. So the alpha TSS should be time-locked to the working memory retention. Otherwise, counteracting effects may be induced by TSS applied during the encoding and retrieval. Given the above background, we can conclude that the conventional TSS method cannot complete our mission during the two limitations presented in the left panel. This idea motivated our desire for a novel TSS system with the following two requirements. First, a capacity to support online phase locking between the externally applied TSS and the current alpha oscillations. Second, a capacity to induce the short during TSS time-locked working memory retention in each cell. In the present study, we first developed a phase-corrected closed-loop TSS system that meets the above two requirements. Which, with this help of this system, the in-phase TSS and anti-phase TSS applies specifically during the retention interval of a working memory task. This allows us to directly investigate the following two research questions. The first one is whether parental occipital alpha oscillations exert the causal impacts on working memory retention. Secondly, we want to test whether the phase difference between the TSS and the endogenous brain rhythms to modulate the effects of TSS. Considering the involvement of the frontal parietal alpha sequestration in memory retention, we hypothesize that comparing in-phase alpha TSS, the anti-phase alpha TSS would suppress working memory performance, parietal alpha power, and frontal parietal alpha synchronization. Now we come to the method section. Illustrated in this figure, the online phase-corrected closed-loop TSS system consists of an EEG instrument recording brain oscillations and a computer exciting the online phases of brain oscillations to decide the time of TSS, and a custom-designed TSS stimulator which communicates with the computer to regulate the application of TSS to the human. Then we use the online phase correct closed loop TSS system to modulate alpha oscillations during the retention interval of working memory tasks. The left panel shows a standard 10 to 20 electrode system used in this experiment. The right panel shows an example of alpha wave detection and the application in the in-phase alpha TSS. 2 mA TSS and the individual alpha frequency was applied over the central parental occipital cortex with the return electrode over the right shoulder. The raw EEG data was stored in a moving time windows. When two consecutive peaks exciting the threshold was detected. Simulation was triggered and lasted for 0.8 seconds. Before the formal experiment, we evaluated the accuracy of phase-corrected closed-loop TSS system. For the phase alignment, for both in-phase TSS and anti-phase TSS, the time delay was near to zero. Let's move on to the description of the experimental procedure. There are 3 TS conditions in our experiment, including the in-phase, anti-phase, and random phase. Each participant perform each TSS conditions separate and at least 3 days in counterbalance order. The Sternberger task was chosen in this study because of this suitability for separating the 3 different sub-processes of working memory. Within each session, spontaneous EEG was recorded during the retention interval of the Sternberger task in the first block, namely pretest, to calculate the IF as the stimulation frequency individually. Then the participant performed 3 TS EEG blocks, namely during one of Sternberger task. EEG data during the retention of each trail was monitored, and the online phase corrected closed loop TSS was triggered once the EEG signal met requirements. To explore the potential duration dependent effects of the phase correct closed loop TSS, another 3 TSS EEG block named during 2 was performed with the design and the TSS parameter same as the during 1. Finally, after experimentation, participant completed the final block of the Sternberger task named the post-test with the EEG code. 39 subjects attend our study. To measure the behavior performance, we calculated the rate correct score, namely RCS. RCS reflects the number of correct response per second and is more reliable than the single measure of the retention time or accuracy. For EEG state, we mainly analysis of alpha power and the PZ electrode and the frontoparental alpha synchronization index for the phase lag index. Okay, let's see what we have found. Inconsistent with our hypothesis, compared to in-phase TSS, anti-phase TSS significantly impaired working memory performance and suppressed the alpha power and the PZ electrode and the frontoparental alpha synchronization and their during 1. The different effect between the in-phase TSS and anti-phase TSS indicates the phase difference do affect the TSS-induced behavior and physiological effects, and also provides the direct evidence for the causal role in parietal alpha oxidation in working memory condition. And during 2, all these differences were not significant. The reason will be discussed later. Next, we investigate whether the modulation of the alpha activity related to the working memory performance at during 1. In phase TCS-induced changes in RCS was positively correlated to the in-phase TCS-induced change in the alpha power and PZ electrode and the frontal parietal alpha synchronization. Further support that the causal role for the alpha acceleration in working memory retention also suggests the frontal parietal alpha synchronization contributes to working memory, lie with the important role of the frontal parietal regions for attention functions. Moreover, there was a significant difference between the correlation coefficients in in-phase TCS and antiphase TCS, which further supports the different effect of the in-phase TCS and antiphase TCS. We mentioned earlier that the impairment during 1 disappear during 2. To explore this reason, we compare the RCS and EEG metrics between the during 1 and during 2. In antiphase TSS, the decreased RCS, parietal alpha power, and the frontal parietal alpha synchronization during 1 was significantly improved during 2. This result suggests that no difference on the working memory performance and during 2 may be due to the rebound following the antiphase TSS-induced surprise effects. Exploring the reason for this rebound need more direct evidence in the field study. To increase the reliability of the attribution of change in working memory performance to the modulation of parental alpha oscillations during working memory retention, rather than the general effect of TSS independent of frequency, we conduct a control theta TSS experiment to modulate brain oscillation not involved in working memory retention. We found that no effects of the theta TSS on working memory performance as hypothesis. Now let's conclude our finding in our study. By modulate parental alpha oscillation during the working memory retention, we provide the direct evidence for a causal link between parental alpha oscillations and working memory retention. We also provide the first direct experimental evidence for the impact of the phase difference on the direction and the magnitude of TSS effects. This evidence also calls for the consideration of the phase difference in the further TSS study. In addition to the scientific contribution, our study also makes great advance for the development of TSS technique. Compared to the conventional TSS, our online phase corrected closed-loop TSS system shows a unique and high valuable capacity to induce or suppress the target auditory activity with a relatively short period of time, rather than the sole entrainment effects. It's definitely going to have a huge application impacts on both basic scientific research and on development of clinical treatment. That's all. Thank you for attention.
Good morning, everyone. I am Qi Li, and from Changchun University of Science and Technology. Today, I want to introduce our study about the effects of temporal and spatial reliability on multisensory audiovisual integration. This is contents. First, what is audiovisual integration? We are bombarded with information from multiple sensory organs during our everyday life. Human brain can automatically combine the task relevant information from anatomically different sensory pathway to form unified percept. Behavioral results have indicated that response to audiovisual stimuli are more rapid and accurate than those to either unimodal visual or auditory stimulus. In addition, multisensory neuron in the superior colliculus can integrate information from different modalities when presented with multimodal inputs. So the temporal and spatial factor are two fundamental properties of multisensory audiovisual integration. Some studies showed that a task-irrelevant sound can be integrated with a simultaneously presented visual stimuli and enhance the visual perception. Moreover, the audiovisual integration complies with the spatial and temporal rules. However, the mechanism remains unclear. We hypothesize that reliable spatial-temporal relationships between visual and auditory stimuli influence behavioral facilitation during a visual discrimination task. So, the aim of present study is to investigate the effects of temporal and spatial reliability of task irrelevant sound on visual perception. Figure A showed the presented sequence of a trail event. After 750 to 1250 milliseconds, a visual stimulus or audiovisual stimulus is presented in the left or right side with equal probability. Subjects were required to look directly at the centrally presented fixation point at the bottom of the screen and attend to the visual stimuli, while ignoring all auditory stimuli. Subject's task is to discriminate whether the presented stimulus was a horizontal greeting or a vertical greeting, and press the left button when the vertical greeting appeared on the left side, and to press the right button when the vertical greeting appeared on the right side. And there are 3 experiments in this study. Figure B shows the stimulus types and the counts for different types across the 3 experiments. There are 2 subtypes of V stimuli and AV stimuli in any of the 3 experiments. For AV stimuli in experiment 1, the auditory stimulus was always simultaneously presented in the same side with the visual stimulus. Therefore, the auditory and visual stimuli maintained a reliable spatial-temporal relationship. Experiment 2 is similar to experiment 1, but the SOA of audiovisual stimuli varied. In half of the AV stimuli, the sound was asynchronously presented with a visual stimulus. For the other half, they were synchronously presented. Because of the variability, the task irrelevant sound didn't provide reliable temporal information for visual discrimination. Experiment 3 was also similar to experiment 1, but the spatial relationship of the sound and the V stimulus within AV stimulus was varied. In half of the AV stimuli, the sound was presented in the opposite side as a visual stimulus. For the other half, they were in the same side. Thus, the sound didn't provide reliable spatial information for visual discrimination. And during data analysis, only the V stimuli and the spatial temporal congruent AV stimuli were of interest in any of the 3 experiments. This page shows the behavioral results. The results showed that response to audiovisual stimuli are more rapid and accurate than those the unimodal visual stimulus. Next, we computed the facilitating intensity. The facilitating intensity was expressed by subtracting RTs for AV target stimuli from RTs for V target stimuli, and HRs for V target stimuli from HRs for AV target stimuli. We found the facilitating intensity in experiment 1 were significantly larger than those in experiment 2 and 3, and no difference was found between experiment 2 and 3. Response biases and sensitivity for visual detection were computed using single detection theory. The results showed that response values for AV target stimuli were significantly lower than those for V target stimuli in any of 3 experiments. Interesting, the sensitivity values for AV target stimuli were significantly higher than those for V target stimuli in experiment 1. There were no difference in experiment 2 and 3. We adopted a similar experiment design and conducted an ERP experiment. The picture showed the overlapping of grand average ERPs to simultaneously presented AV stimuli in experiment 1 and 2. Although the ERP were similar between the 2 experiments, significant differences were observed. The gray squares indicate the time periods in which the ERP response was significantly different between experiment 1 and 2. The figure showed the scalp topographies of different waveforms formed by subtracting the ERP in experiment 2 from those in experiment 1. And there was a significant difference in amplitude in 3 main areas, A, B, C. The figure shows the overlapping of grand averaged ERPs to simultaneously presented AV stimuli in experiment 1 and 3. Similarly, the gray squares indicate the time periods in which the ERP response were significantly different between experiment 1 and 3. The picture shows the scalp topographies of different waveforms formed by subtracting ERP in experiment 3 from those in experiment 1. And there was a significant difference in amplitude in three main areas, A, B, C: the central area, the anterior area, and the parietal occipital area. In addition, we conducted fMRI experiments to investigate the effects of temporal reliability of sound on cross-modal facilitation of visual discrimination. The fMRI results showed the contrast image which were generated for AV stimulus, various V stimulus in experiment 1, in which the task's irrelevant sound didn't provide reliable or temporal information for visual perception. The MTG, STG, PAC, and IFG were activated. The fMRI results showed the contrast images which were generated for AV stimuli, various V stimuli in experiment 2, in which the task's irrelevant sound provide reliable temporal information for visual perception. The MTG, STG, PAC, PVC, and LOC were activated. The effects of temporal reliability of sound on cross-modal facilitation of visual discrimination were inspected by the results of EXP2 versus EXP1 contrast. The only differently activated brain region was the bilateral LOC. The regions of interest ROI were constructed in the bilateral LOC. The results showed more creased bold single change in bilateral LOC in EXP2 contrast than in EXP1 contrast. Conclusions: reliable spatial temporal relationships within audiovisual stimuli were required for audiovisual integration. Implicit linking of visual and auditory stimuli is enhanced by spatial temporal reliability within an audiovisual stimulus, resulting in multisensory integration and behavioral response facilitation. Implicit audiovisual integration may operate in a top-down manner at a relatively late processing stage. The LOC is responsible for cross-modal associations based on the reliable temporal relationships within multisensory stimuli. That's all. Thank you very much for your attention.
Hello everyone, good morning, afternoon, and evening. I will present a topic of exploring fatigue induced by motor imagery-based brain-computer interface control. This work is done in Shanghai Jiao Tong University. Today my talk includes 4 parts. First, I will give you a brief introduction about the research background of fatigue and BCI. Then I will present experimental design of inducing fatigue in a motor imagery-based BCI control. In the third part, there will be data analysis and results for behavioral and electrophysiological data. And part 4 shows the conclusion of this study. So various previous research shows that when a cognitive task is repeated over a long time, considerable mental effort is required. Thus, error rates might increase and the subject could report a sense of mental fatigue. For example, Leonard and Trijo designed an experiment of solving mathematical problems, as they asked their participants to solve the math problem as soon as possible until they quit from exhaustion or 3 hours has passed. After analyzing the behavior data, they found their subjects' response time increased, and the error rate did not change significantly. On the other hand, the grand average EEG power spectral and topographic maps of peak frequencies in the theta band and alpha band showed a consistent increasing trend across different periods of the task. Lin Yao and his colleagues showed a study that 2 monkeys perform a vigilance task. The monkey has to touch a switch within a proper time after the go cue appears in order to get a juice reverse. The reaction times of correctly performed trials are plotted in black dots. The smoothing green line is an estimation of the task performance. As you could observe, the number of correctly performed trials decreased. The average power spectral of an ECOG electrode at FC is shown in the subfigure C. Roughly, the theta and alpha band power increase when the error rate increase. Further analysis of the power spectrum of the correct and incorrect response trial in each ECOG electrode is shown in figure 2. Clearly, we could see higher spectral power of theta and alpha band for incorrect trials compared to the spectral power of correct trials. This indicates that performance have decreased as the task is performed repeatedly over a long time. Mental fatigue might be induced across the time. Global increase of the theta and alpha power across the whole brain might be an indicator of the mental fatigue. So brain-computer interface is a novel technology which can directly decode a person's intention from her or his neural signals. Motor imagery-based BCI and SSVP-based BCI were commonly used to non-invasive BCI paradigm, which has been mentioned in a few presentations in this workshop. Both modalities provide certain information transfer rates. In prolonged operations, fatigue might arise. Although fatigue might affect the performance of BCI, it worth investigating. Charlton and his colleagues evaluated the fatigue in the SSVP-based BCI. They found increasing in alpha band power and theta alpha band power are associated with the increasing of fatigue level. The amplitude and SNR of the elicited SSVP might be reduced due to users' fatigue. Fatigue might have negative effects on SSVP-based BCI's performance. However, in this study, the authors didn't mention whether online SSVP BCI is performed, and it seems that no feedback is provided to the subjects. Based on the previous research literature, our research objectives to investigate the fatigue effects on the motor imagery-based online BCI. So we used a left-hand versus right-hand mental imagination to perform the 1D cursor control. Each subject was required to finish 4 sessions of the experiment, including 1 training session and 3 experimental sessions, with various resting rates. In the training session, subjects were instructed to be familiarized with the MI-BSI task. Each subject finished 3 experimental sessions in different days, and the resting approach was arranged in a pseudo-random order. Each session consisted of 400 trials in total. 3 different resting conditions are designed as follows. In the no-rest condition, 201 to 400 trials were immediately followed after the first 200 trials. In the other 2 resting conditions, subjects have a period of 16 minutes eyes open or eyes closed resting period at the beginning as well as at the end of each session. Multidimensional fatigue inventory, that is MFI, and short stress state questionnaire, that is SSSQ, were used to measure subjects' fatigue level. This figure shows the experimental design of a single trial structure. We ask them to perform motor imagination in order to generate the proper control signal. Then the EEG signals from their scalp was continuously acquired, computed, and translated into command signals to control the movement of the cursor. Since the subjects received the online feedback, we applied an online adaptive classifier to compensate the non-stationary of EEG features. This online feedback and adaptive classifier might affect the negative effects of fatigue to BSI performance in a complex way. Thus, we will try to analyze the change of 2 commonly used features in order to separate the effects of an adaptive classifier. This is a pipeline of our analysis. Artifacts were corrected with the artifact subspace reconstruction approach. The signals were bandpass filtered into 0.2 to 45 Hz. Then the data were downsampled to 200 Hz, and independent component analysis was performed on the data of each session to further remove artifacts. We will analyze the results of the questionnaire, BCI behavioral performance, including the percent valid correct and information transfer rate. Lastly, we will contrast the change of power spectrum between prior to and post-resting periods. ERD, ERS, and ERP comparisons between prior to and post the resting period to be analyzed as well. Next, I will present the data analysis results. Here's the group average difference of the SSSQ, that is stress questionnaire. Scores between prior to and post-resting period were shown in the left upper figure. The average scores of engagement decreased in all 3 sessions, and the statistical analysis revealed that the difference was significant in the no-rest session. There was a significant increase of distress in the eyes open rest session. For the multidimensional fatigue inventory, the average score of general fatigue increased in all 3 sessions, and there were significant variations in eyes open rest and eyes closed rest. Mental fatigue also increased in all 3 sessions, and there were significant variations in the open rest and eyes closed rest. The average BSI performance of all subjects across 3 sessions was shown in the second row of this figure. The PVC and ITR of each session prior to and post resting period did not show any significant changes. The change of band power in the first 100 trials was shown in this figure. No significant change was found in the theta power, but for alpha power in channels located over sensory motor area, we find significant increase. On the contrary, beta band power over frontal area increased the most. Further analysis revealed that the alpha band power variation for each session was shown in this figure. The first row showed that the alpha power of most channels increased in all sessions, regardless of the rest type. The second row of topographies showed the differences of variation between sessions. The effect of eyes closed rest was significantly different from other sessions, which means in the right target task, eyes closed rest had an inhibitory effect against the increase of the alpha band power at the preto-occipital area. The alpha band power variation of left target task for each session were shown in the first row of this figure. The average change of alpha band power was basically consistent with the right target task. The second row of this figure shows the variation differences between sessions. The effect of rest was statistically different between the other two sessions for left target task. At the preto-occipital area, both eyes open and eyes closed resting ways had inhibitory effect against the increased tendency of alpha power. However, eyes closed rest had stronger effect than eyes open rest. The average ERP amplitude during the 300 plus minus 50 microsecond period after target appeared was given in the first row of this figure, while the average ERP amplitude after cursor appeared was shown in the second row. The ERP amplitude mainly maximized in the occipital area, and it showed a lateralization in most conditions. From this topography, a decreasing trend of ERP amplitude could be observed. Based on the observation, we investigated the statistical comparison of ERP amplitude between prior to and post the resting state period. The average ERP amplitude for the 201 to 400 trials was weaker than that of the first 200 trials. For the right target, the analysis of ERP amplitude in channel PO3 indicated that the ERP caused by target appears significantly decreased in no rest session during right target trial. However, for the left target, the analysis of the ERP amplitude in channel PO4 indicated that the ERP caused by the target appears significantly decreased in no rest session compared to eyes closed resting approach. ERD of C3 and C4 channel in the first 200 trials for all sessions were shown in subfigure A. The absolute amplitude of ERD for both C3 and C4 were stronger in the first 100 trials, while C3 had a greater ERD than C4, which was reasonable during a right-hand motor imagery task. The topographic map of variation and the statistical analysis results are shown in subfigure B. It also proved that compared with the first 100 trials, ERD of the 101 to 200 trials decreased on both sides for tasks of right target. However, in the control of the left target, no ERD for any channel showed significant variation. An interesting phenomenon was found during the rest. So the band power change of the theta, alpha, beta were analyzed separately. The contrast power change between two different periods were shown in the topographies. First, for the theta band power, it had significantly increased during eyes closed rest, but the theta band power remained basically unchanged during eyes open rest. The alpha power under eyes open rest kept no significant change across the session. The change of alpha band power displayed a different tendency under eyes closed rest. During the eyes closed rest, an increasing trend was found in the first 110 seconds, while the last 850 seconds had a decreased trend. This phenomenon showed a statistical significance in all the channels. So analysis of the change of the Fisher scores and mutual information with respect to band power features of the last 200 trials versus the 200 trials were shown in figure A and B. We did not see any significant change of feature separability due to prolonged BCI operation. Thus, this analysis might suggest fatigue might not significantly affect the BCI performance in this study. So the fourth part is the conclusions. So our conclusion is that first, prolonged motor imagery BCI operation might have effects on the electrophysiological indicators and mental states, but the effect on the BCI performance is not significant. The alpha band power in sensory motor area has an increasing tendency, but the ERD modulation level seems to decrease. The ERP was found asymmetric and seems to decrease over time. And the third point, the eyes closed rest caused alpha band power increase and a subsequent decrease during resting state, and has a stronger effect than eyes open rest on inhibiting the increasing of alpha band power in the parietal occipital area. So my talk ends up here, and I'm ready to take up any questions. Thank you.
Hello everyone, it is my great honor to be here to present our recent work on the title of Hybrid Unsupervised Handcraftage and Deep Feature Characterization and Fusion for EEG-based emotion recognition. Today's presentation will be outlined as follows. We will first present our motivation and research background. Then we will report our works on emotion dynamics representation and emotion dynamics decoding. Finally, a conclusion will be given at the end. For the research background, in the affective computing field, an embedding of brain-computer interface technology could be very helpful to boost the development of affective computing techniques for real-world application. These types of techniques could be used for real-time emotion monitoring in portable intelligent device. It could be employed for early screening of mental health disease in medical assessment systems. Furthermore, it could be used in a closed-loop emotion regulation system for medical intervention and treatment. However, there are several barriers in the development of BCI-based affective computing techniques. For example, individual difference problem. The brain response could be quite different for different persons, even corresponding to the same emotion stage. For the same person, the brain reaction could change after a certain time period. On the other hand, EEG data are very weak signals and sensitive to the environment variations, which are easily contaminated with the noise. To tackle the existing problems, we will conduct our works from two directions. The first one is emotion dynamics representation, in which the data validity of EEG data for emotion study will be examined. The second one is emotion dynamics decoding, in which the solutions for individual difference and label missing problem will be presented. The model effectiveness on cross-subject EEG-based emotion recognition application will be discussed. Our research work are conducted on DEAP database. In this database, total 32 subjects were invited to watch 40 music videos, which were presented in a randomized sequence. The EEG signals are simultaneously recorded during video watching using 32 EEG channels at a sampling rate of 512 Hz. For each trial, it was composed of 4 stages: resting at the pre-stimulus stage, video watching at the video stimulated stage, resting at the post-stimulus stage, and subjective feedback at the self-assessment stage. Next, we will present our work on emotion dynamics representation. In this work, 2 questions are raised. First, whether EEG signals could be efficiently reflect emotion dynamics. Second, whether multimedia stimulation could efficiently trigger emotion dynamics. To answer these two questions, the comprehensive relationships among emotion dynamics, EEG signals, and multimedia contents are studied. This is an overall framework. The emotion dynamics analysis is conducted under the exploration of emotion task effect, level effect, and the evoking dynamics on brain response. The multimedia stimulation effect analysis is conducted to investigate the emotion stimulation effect of visual contents, audio contents, and timing effect on brain response. EEG microstate analysis is introduced to categorize brain dynamics during emotion induction. A standardized EEG microstate analysis is implemented as the given flowchart, including GFP calculation, topography extraction, microstate detection, backfitting, and feature extraction. The final extracted microstate features could be used to quantify dynamic changes of brain spatial-temporal activities. In the microstate analysis, microstate detection is a fundamental and essential part that will directly affect the validity and reliability of further analysis. We found that our current microstate detection method is very sensitive to the variations of subjects and experimental conditions. To tackle this problem, we propose a sequential microstate clustering analysis for efficient and representative EEG microstate template detection. It consists of two-step clustering. The first clustering is implemented in the within subject level to extract individual representative microstate topographies. The second clustering is conducted in the cross-subject level based on the extracted subject specific microstate topographies. Comparing to the previous EEG fMRI studies, it's found that the final detected four macrostates show similar topographic configurations with four functional brain networks, including audio network, visual network, default mode network, and dorsal attention networks. In general, the first two networks are more associated with low-level brain functions, while the last two networks are closely related to high-level brain functions. We evaluate the emotion task effect by measuring the pairwise statistical difference of EEG microstate activities between pre-stimulus and post-stimulus stages. It is found that a significant increasing trend is observed in MS2 and MS4, and a significant decreasing trend is observed in MS3. The transition from MS3 to MS2 and from MS4 to MS2 significantly increased after emotion task manipulation, while the transition from MS4 to MS3 significantly decreased. The emotion level effect on brain response is examined on two independent emotion dimensions, valence and arousal. For valence, the results present a lower MS4 is observed in the high valence group, and a greater transition from MS1 to MS2 and a lower transition from MS1 to MS4 are observed in the high valence group. For arousal, greater coverage and occurrence of MS3 are found in the high arousal group, and a greater transition probability from MS2 to MS3 is observed in the high arousal group. The microstate difference from moment to moment are also evaluated as the temporal variation of emotion evoked EEG dynamics. Here, each gray line indicates the brain response corresponding to one video, and the black line in the middle is an average of brain response across all videos. It shows different multimedia stimulation evoke different temporal dynamics of brain response. To better understand the temporal dynamics of brain response during video-based emotion evoking, we conduct multimedial stimulation effect analysis and explore the emotion triggering relationships between EEG microstate dynamics and multimedial stimulation contents. For visual contents, both low and high visual features are categorized. For low-level visual features, a positive correlation is found between brightness and MS4, and for high-level visual features, a positive correlation is observed between the visual features extracted as the deep convolution layers and MS4. For audio contents, both low-level and high-level audio features are also categorized. For low-level audio features, a negative correlation is observed between low-level ZCR feature and MS3 occurrence. And for high-level audio features, a positive correlation is found between the audio features extracted from Convo5 layer and MS3 coverage and occurrence. To measure the time effect, we shift the multimedial stimulation in a preceded or succeeded direction. For visual content, the results show a valid time effect with EEG response is in the range of -100 to 400 milliseconds. The highest correlation is reached at 0 millisecond, referring to stimulation onset effect. For the audio contents, it is found that a valid time effect with EEG response is in the range of 0 to 600 milliseconds. The highest correlation happens at 200 milliseconds, which shows a post-stimulus effect. The above results verify the EEG signals could efficiently reflect emotion dynamics. Also, multimedial stimulation could efficiently trigger emotion dynamics representing on the simultaneous collected EEG signals. It is found awareness is more correlated with MS4 and arousal is more correlated with MS3. Visual stimulation is more related with MS4 and audio stimulation is more related to MS3. Next, we will present our proposed decoding model for EEG-based emotion recognition. Here, also two questions are raised. First, how to solve individual difference problems in EEG-based emotion recognition. Second, how to solve label missing problem in EEG-based emotion recognition. To answer these two questions, we conduct an unsupervised deep learning model with hypergraph theory. In this model, we propose an efficient hybrid deep encoder-decoder network architecture termed as EEG FuseNet for categorizing non-stationary time series EEG signals. The proposed EEG FuseNet incorporates different sources of feature information through integrating CNN, RN, and GAN in a smart hybrid manner. Specifically, based on the features extracted by CNN from raw signals, RN is adopted to enhance the feature representation by exploring the potential feature relationships at temporal adjacencies. To improve the training performance, GAN is incorporated to improve the training process of the CNR network through dynamic updates in an unsupervised manner, which is potentially beneficial to high-quality feature generation. To solve cross-subject EEG-based emotion recognition under label missing condition, we introduce hypergraph to realize emotion classification in a pure unsupervised manner. Different from a simple graph, a hypergraph is capable of connecting a couple of vertices, in other words, more than two vertices that share similar properties. Thus, more general types of relationships could be presented and reveals more complex hidden structures than single connections. In the implementation, the EEG samples are treated as vortices and a hypergraph is constructed based on the relationships among these vortices in terms of EEG characteristics. Here are some definitions in the hypergraph theory. The emotion classification is realized by partitioning the constructed hypergraph into a specific number of classes through computing the hypergraph Laplacian and solving it with an optimal eigenspace. The constructed hypergraph is then divided into a number of classes, and each class indicates one emotion state. We compared our proposed method with the conventional features in the application of cross-subject EEG-based emotion recognition across 4 different emotion dimensions: awareness, arousal, dominance, and liking. The results indicate that the proposed method achieves the best performance across all 4 emotion dimensions. Both recognition accuracy and F1 score are significantly higher than the conventional features. Besides, we evaluate the robustness of the proposed method by comparing to the state-of-the-art decoding methods with the same feature input. The results also show that our proposed method achieves the most robust results across different emotion dimensions. The effectiveness of the proposed EEG FuseNet is fully validated in an ablation study. The results show that the proposed method outperforms these variant models, for example, CNN-based, CNN-GAN-based, and CNN-RN-based. The proposed method is more capable of characterizing and fusing emotion-related deep EEG features in a high quality and achieving better cross-subject-based emotion recognition performance. This work verifies the possibility in solving the individual difference problems in an unsupervised manner. Even the labeling information is missing. Finally, a conclusion is given here. In today's presentation, 2 main concerns in EEG-based emotion recognition applications have been verified. First, the validity of EEG signals for emotion study has been verified through the dynamic relationship exploration among emotions, EEG activities, and multimedia contents. Second, a robust and reliable unsupervised decoding model is proposed that realizes EEG-based cross-subject emotion recognition in a pure, unsupervised manner. Thank you very much for your listening. Thank you all the speakers for their impressive presentations. Now we are open for the questions. Thank you.